Hello everyone, I'm Nicholas, and today we're going to talk about the optimization of lincomycin production, and this presentation was made by Moses Himawan, me myself Nicholas, Sebastian, and then William Posada. So we're going to talk about the introduction of the product itself, the lincomycin production process, and finally the product optimization method. First of all, the introduction. So here is our product, lincomycin. It's basically the part of the lincosamide antibiotic and is effective for a wide variety of bacteria. It is divided into lincomycin A and lincomycin B, whereas lincomycin A has better activity than lincomycin B. It is also much more safer than lincomycin B because it has less toxicity. It is also typically synthesized by Streptomyces lincomyces as secondary metabolite.
Next is the lincomycin production process. So here's the basic lincomycin production flowchart, and here's the cell isolation. The S-linconysis can be bought from DSMZ or isolated manually from soil and water. If it is isolated manually, humic acid vitamin agar is used to effectively grow the bacteria. Then gram staining of visual section can be performed to confirm the S-linconysis. Additionally, the most accurate method is 16S or RNA sequencing. Then the bacteria is inoculated into an So here's the cell growth process. Initially, S-linconysis is grown in petri dish until it reaches the exponential phase. Then the cell culture is transferred into a 250 ml press to increase the cell concentration. And lastly, 1/10 of the cell culture is inoculated into a bioreactor, while the remaining cell culture is stored for future.
And now I'll be discussing about the fermentation of lincomycin. For the fermentation, continuous stirred tank bioreactor have been chosen as the bioreactor used for the fermentation of lincomycin. There's a few factors that must be considered, which is 1. Oxygen concentration, 2. Stirring speed. High stirring speed may increase oxygen concentration but may cause cell disruption, formation of foams, and heat generation. Third is temperature. The range of 18 degrees Celsius and 45 degrees Celsius are the range of temperature that can be used, and the optimum temperature are 30 degrees Celsius. And finally, acidity, with pH 7.5 being the optimum pH. Cell disruption is done using high frequency wavelength using an ultrasonic homogenizer. It must be done in low temperature in cold water bath. Once the cells have been disrupted, the recovery must be done. First, wash the mycelium with distilled water. This has diffused to remove cellular protein. Place in affinity chromatography with resin and then dry the solution at high heat and crystallize the solution. And after that, purification is done to separate lincomycin A from lincomycin B. Our target is lincomycin A, though this method also allows us to separate for lincomycin B as well. Which is A, you need to dilute the crystal in methanol. Add the chromatography column with silica gel with C18. Stir the solution at high heat. Add methanol and ethyl acetate and adjust pH with HCl. Cool the mixture until 4 degrees Celsius. And then for lincomycin B, simply repeat the 4 steps to extract the lincomycin B as well from the solution after lincomycin A.
Now we go on how to optimize lincomycin production. Here are some methods can be used. First one is calcium gluconate addition. The addition of calcium gluconate provides 41.3% higher yield compared with untreated strain. Next is the strain selection. Different strains produce different amount of lincomycin. Mutant strains 1020 gives 10% higher yield compared with S-linconysis 5520. S-linconysis 075 provides 6,634 U per milliliter yield, and Streptomyces lincomyces mutant 2 gives 8,126 U per milliliter yield. Another comparison between Streptomyces lincomyces M4018 and industrial strain. The M4018 provides 146% yield compared with the industrial one. Lastly, we could do some genetic amplification on LMB1 gene and LMBU gene, or add a co-expression of METK1 and METK2 to optimize lincomycin production.
Next is nitrate and amino acid supplementation, in which when you give nitrate supplementation, it will increase the production of lincomycin by 50%, while L-proline, L-tyrosine, and L-alanine supplementation will give a result of 23%, 10%, and 30% increase of lincomycin respectively. Next is the statistical media optimization. It is found that when you give the media 25 gram per liter soybean powder, 1.4 gram per liter constitutes liquor, 126 gram per liter glucose, it will result in more or less 4,600 mg per liter lincomycin A. Now, what is important here is that it results in more or less 0.8% lincomycin B, which is a very low amount, and that is precisely what we want in this case. Finally, there is the aqueous-to-phase supplementation with the purpose of separation of lincomycin A. It has the advantage of reduced cost and simpler operation, however, it has operation efficiency. Here are our references. Thank you for your attention.